Hello everybody, this is Emanuele from University of Milan. Today I'd like to tell you about our recent work on understanding the large-scale clustering of the galaxy power spectrum in Fourier space and its connection to primordial non-Gaussianities. I don't need much of an introduction for this audience, but let me just remind you that the initial conditions of the universe have certain properties which are crucial for the standard cosmological model to fit any data, CMB or large-scale structure data. And in particular, we'd like to understand more about them because they have some very special features. And so the idea of this talk is to first just clarify why we do care about primordial non-Gaussianities and how we can measure them in the power spectrum. And so discuss what is the estimator we use on actual data. And once we've clarified the underlying theory, then we can have a look at the most recent constraints on local primordial non-Gaussianities that we obtained a few years ago using EBOS data. So why we care about primordial non-Gaussianities? Because we know that at least in inflation, which is the leading paradigm for producing the initial conditions we observe today, certain features come out basically for free. For instance, the running and the spectral index have certain values. We know the initial conditions are approximately adiabatic. And we also know the initial conditions are approximately Gaussian. In particular, this feature is extremely important if we want to understand the dynamics of inflation beyond the free theory, because by looking at the higher point function, we do have access to the dynamics of the inflaton itself and whatever other spectator fields could be around at those high energies. Of all possible higher point functions, the bispectrum is of course the simplest one. And among the configurations that the bispectrum can take, there is one which is special compared to others, which is the squeeze limit of the bispectrum, which is shown in this triangle here. And in the squeeze limit, there is a theorem by Maldacena and later generalized by Creminelli and Zaldariaga, which says that in single fields Roller models of inflation, local primordial non-Gaussianities are exactly zero. So we do have a strong theory, goal, and benchmark that we would like to achieve, because by detecting local primordial non-Gaussianities, we can exclude all single field models of inflation. So far, the best way to look at local primordial non-Gaussianities has been through the bispectrum of the cosmic microwave background. And local PNGs are usually parameterized by these following ansatz for the primordial curvature perturbation zeta. So we say that the primordial curvature zeta is the sum of a Gaussian piece plus a non-Gaussian one, whose amplitude is parameterized by one parameter FNL local. Given that the smallness of the curvature perturbation in the early times, the current constraints on FNL local tells us something which I think is quite underappreciated in the community, which is that the local primordial non-Gaussianities are the best measured parameters in cosmology after the temperature of the CMB monopole. So as I was saying, detection of local PNG will rule out all single field models of inflation, but non-detection of local primordial non-Gaussianities will also tell us something, because in most models of multi-field inflation, this number comes out over the unity. So by going to this threshold, we can actually start to distinguish between different scenarios for inflation. So the CMB will improve a little bit in the future, about 30%. And so the hope is that really large-scale structure could sort of take over and bring us to the theory benchmark of uncertainty of order 1. Nowadays, as I will show you later in this talk, the uncertainties are of order 25. So we really have a long way to go before we get there. So the question is how we do get there and how we can be sure that we're doing this right. So in the large-scale structure, there is one way we can measure primordial non-Gaussianity, which is by looking at the scale dependence of galaxy bias at very large scales. Because in the current understanding we have of structure formation, galaxy bias is nothing else than the response of galaxy number density to the presence of long wavelength modes. In a universe which is Gaussian and the equivalence principle holds, and we do have some symmetries like rotational and translational symmetries of the correlators, then basically we can write down all sorts of operators that we can think of in this bias expansion. And in a Gaussian universe with the equivalence principle, the first two of these operators are actually zero, because we cannot be sensitive to the actual value of the gravitational potential and not into the gradients of the gravitational potential. This picture is slightly modified if we now have primordial non-Gaussianities. Let me just guide you through the argument why this is so. So the way of thinking about this is that we now want to split all perturbations in long wavelength and short wavelength, and in particular we want to do that for the gravitational potential. And then we plug the splitting into these ansatz for the local shape. And if we work it out to linear order, we find out that there is a coupling between the large scales and small scale gravitational potential, which would not be there in absence of primordial non-Gaussianities. Just to remind you, what you all know, that the relation between the gravitational potential and the density fluctuation goes through the Poisson equation. And so this term picks up k to the minus 2 dependence when we calculate the bias. So we take our expression, we plug it in a definition of linear bias. So this is the response of the number density to the long wavelength density perturbation, which are now coupled between small and short scales by the presence of FNL. So when we take this derivative, we do have a standard piece, which is the linear bias. And now there is another piece, which has to do with the variation of the number density of galaxies with the modulation of the amplitude induced by primordial non-Gaussianities. And so schematically, we can write that the total bias is the sum of a Gaussian piece plus a non-Gaussian one. And if we go to very large scales, larger than the quality scale, then this looks like a k to the minus 2 dependence with an unknown free parameter, which is this p phi. So by looking at large scales, we can actually measure primordial non-Gaussianities. So the question is, how do we want to measure those large scales? And so we could write a theory like the one I'm writing here. So this is just linear theory plus linear Redshift space distortion. And I've added an FNL parameter, and I've also added some noise. And so if you look at how the theory shows up in this configuration, then the comparison between FNL of 0 and FNL of 1 reveals that the difference we're actually looking for is extremely tiny. And if we now put the unexpected cosmic variance from a survey like Euclid, then we see that this is going to be extremely challenging to get there using power spectrum alone. On top of that, there are other issues that we need to understand if we want to model the large scale properly. One of them has to do with the systematics which affect measurements at large scales, for instance, foregrounds, or poor understanding of window function or selection functions. And on top of that, which is the focus of this talk and also of Enea's talk, which I encourage all of you to go and watch, is that the theory which I've just written here is actually not the right theory to describe the large-scale clustering of galaxies. So let's just look at this first part. So how can we predict the galaxy power spectrum on large scales? So we're given some catalogs of galaxies from the collaboration, which contains positions in angular coordinates and redshift of each object, of each galaxies. And given this catalog, we can compute any two-point statistics that we want, as long as we can predict it. So in particular, for spectroscopic surveys, which is the focus of my talk, I would like to give you my 2 cents on what I think is sort of the best practice. My preference is always to choose the lower dimensional data vector, which is the one for which the nonlinear theory is very easy to write. And so what I'm saying is that we should go towards making the life easier for the people actually measuring things on the data. And then on our side, we just have to work out the theory for whatever objects we're given. And so what are possibilities that we can consider? So one possibility is, of course, to just look at angular clustering. So we bin our data in redshift slices, and then we cross-correlate them and auto-correlate them, and we look at the CLs. So these are the CL of Z1 and Z2. And in principle, we can also look at the Fourier-Bessel transforms of those. So these are the CLs of K1 and K2. This way of estimating data has certainly some pros. In particular, we don't need to assume a fiducial cosmology because we're working in observed coordinates, which means that we don't have to do any basically operation on our data before we estimate the CLs. And this is also the basis in which the GRFX, which a lot of people in this conference care about, are naturally written. On the other hand, from the measurement point of view, the CLs have certain problems. So first of all, their relation to the nonlinear modeling of Redshift space distortion is not easy. There has been progress over the last few years, but this still is a very open area of research. Most importantly, from my point of view, is that the CLs are not optimal unless you have a lot of very fine redshift bins. And related to this large number of redshift bins is that you end up with the data vector, which is huge. So you can roughly say that the number of data points is going to be the number square of bins, because you need to compute the cross correlation between them, times L max. And so this easily becomes order 10,000, which implies that the covariance matrix has 10 to the 8 entries. And so in terms of inverting this matrix and computing the likelihood, this is certainly not practical, at least nowadays. And so it's not really feasible yet in real analysis of primordial Gaussianities. So the other main player here are three-dimensional analysis. So what we do here is that we convert the positions and angular position and redshift of galaxies into three-dimensional distances. So S1 and S2, for these two little galaxies here, which are now separated by a three-dimensional vector S. And here I'm also indicating the bisector D. So what we can do is we can just measure the correlation function of those objects. And this is a perfectly fine choice. Although for primordial Gaussianities, the problem is that the information is spread out on all possible separations. So we're losing this nice feature of Fourier space where we only have to look at very low K to see the scale-dependent bias. So what we're left with, which is my favorite choice, is to look at Fourier space. The estimator which we usually consider is this one called Yamamoto or FKP estimator, which contains a few key ingredients. So we see here that we have to give the two galaxy density at position S1, S2. We need to average them over all positions. Of course, there is a window function, which just tells us if some galaxy is inside or outside our survey. And then there is a projection, which is kind of a weird one, because we're projecting K over some line of sight, D, of the pair, which we have not specified yet. And it could be actually any line. It could be this bisector here. It could be one of the two pair members. It could be the mean. You have absolute freedom to do that, as long as you can then predict the average of this estimator. So there are certainly important pros of Fourier space. And in particular, the data vector is small. So we do have here only few multiples. Linearities, non-linearities are just written in this language of Fourier space. So we can instantaneously combine BAO and RSD and small scale measurements, which are very important for future galaxy survey. Drawbacks are that we do have to assume a cosmology. So this is the Alcor-Pashinsky effect. This is not a real problem, especially because we now know that the distance redshift relation is extremely tightly constrained by Planck. On the other hand, if we look at this object, it's not really clear what we're actually measuring once we go on very large scales. And the reason I'm saying that is because we know that redshift space distortion on the curved sky and GRFX breaks homogeneity and isotropy of correlation function. So what that means is that if we naively Fourier transform these two galaxy density here, and we multiply them, we obtain a power spectrum which is not diagonal. So this is now a function of K1 and K2. Whereas the object that I'm claiming we would like to measure is only a function of K, of a single K. So we first need to understand what's going on here. And so this is a program that we started a few years ago. And let me just guide you through some of our main results. So first of all, we make this choice that we pick one of the two galaxies at the last line of sight. This is called the endpoint line of sight. And we make this choice from a purely practical point of view, because this is the fastest estimator that we can build and measure using FFTs. So this requires the fewest number of FFTs compared to all others. If we now take the expectation value of this object, so we need to take an expectation value here, we can do Fourier transforms, and then we end up with this expression here. So what we find is that the average of the measured power spectrum is some weighting of the underlying power spectrum of the galaxy density field, which is a function of 2K. And this estimator is doing two things. So first of all, it's averaging over all possible line of sight in the survey volume. So this is given by this integral over D3S1. And then we're also averaging over the off-diagonal entries of this power spectrum. And this is actually a very nice feature because it tells us that once we go to small scales, where the power spectrum becomes diagonal in the plane parallel limited, we are not losing any information. Oops, sorry. Let me go back. Okay. In this formalism, it's not yet clear how we can predict this object. So let me take a few more steps. So the first thing I would like to do is to actually take the correlation function of S1, S2 and write it as a function of pair separation S and S1. And then I can formally just Fourier transform with respect to S and obtain what it's called the line of sight dependent power spectrum, this P of K and S1, which I can then plug into our expression and rewrite the average of the estimator in this very nice form, which tells us that the measurement is nothing else than the average of the local power spectrum over all possible line of sight. And in particular, through this line of reasoning, we arrive to our final conclusion, which is that given a model for the correlation function, which is easy to write, including all GRFX, then predicting the observed power spectrum in galaxy survey boils down to nothing else than a bunch of Fourier transforms. So let me just unpack that for you in its full glory. So here I've written the estimator, I've taken the expectation value of the correlation function, and I'm expanding that in multiples with respect to S1 dot S. And so the final expression is this one, which for those of you who are familiar with the expression for the pseudo-CL in CMB analysis should remind you something, because indeed the two are very similar. And so what we have to do is a Hankel transform, so it's a Fourier transform of the multiples of the correlation function, which are now coupled with the multiples of the window function, which are defined here. And the combination of those that we have to couple is just given by the angular structure of the estimator, and this is a 3J symbol. The S1 dependence in this estimator is there to remind us that, of course, if the redshift bin is very wide, there is also evolution within the bin. This S1 keeps track of that, and it also keeps track of the fact that in GR, a lot of the new effects that enter through projection are actually dependent on the distance to the pair of galaxies. There is another approximation which we always do, and we have to check whether this is a good approximation or not, especially when we look at primordial Gaussianities, is that we can imagine that this redshift dependence of the correlation function and of the multiples of the window function is smooth, because our selection function is smooth. So in this case, we can assume that we can make the approximation of computing the theory at some effective redshift. In that case, we can pull out this CL from the DS1 integral, which we can just integrate over the F of L1. And we arrive to the final formula, which is the one used by all galaxy survey, for instance, BOSS and EBOS. And here I'm taking the extra step of defining perhaps an effective redshift for each multiple, whereas I can also assume that there is one for all multiples, and we also want to check whether this is a good approximation or not. So in this talk, I would like to focus on a few of those effects that enter the calculation of the correlation function, in particular wide angle redshift space distortion and lensing magnification, which is renowned to be a very hard term to include in Fourier space, but now we can just do it out of the box because we have a model for the correlation function. And in Enea's talk, which I also would like to remind you to go and watch, he will show all possible GR terms. He will discuss the cancellation of AR divergences and how all of those interact with the survey window function. So just to give you a feeling of how the prediction look like of the average of the observed galaxy power spectrum. So here you see for each row corresponds to a different multiple. So you have the monopole, the dipole, and the quadrupole of the correlation function from top to bottom. And the different columns correspond to different surveys. So here we are taking the simple approach of considering a survey which covers 1/3 of the sky and has an approximately constant selection in redshift. And the selection goes from some redshift mean to some redshift max. And so the different columns indicate different values of redshift that we're covering. So what you see here is that once we go to large scales, which is the scales where we expect GR effects to start becoming important, the observed power spectrum receives corrections which are of order 1 compared to the plane parallel limit, which is the dashed black lines, and those are due to the presence of the window function. We changed the power spectrum a lot. You can see it here in all these plots. And the other correction that they receive is from the so-called integral constraint, which is shown here in the blue line. And the integral constraint is an observational effect which we always have to take into account on large scales, and arises from the fact that we do not know the underlying true mean of the galaxies that we're observing, but we are rather estimating this mean from the field itself. And so we have to impose that the power spectrum goes to 0 when k goes to 0 by hand. And so this is the so-called integral constraint. And so what you see here is that, for instance, the integral constraint has a huge effect on the quadrupole. So if you look at the difference between the dashed red and the blue, they both include the window function, but only the blue includes the integral constraint. And you see that, for instance, in a lot of cases, this actually makes the quadrupole become negative on very large scales. So these effects are extremely important, and we do expect them to be actually larger than the GR effects of the theory we're interested in. So let's look at the first one I was referring to. So these are wide angle Redshift space distortion. All of you, I guess, are familiar with them. So they arise from the fact that the sky is curved if we look at pairs which are separated enough on the sky. The scale that controls the amplitude of those is what I call R survey, which is a typical large separation within your volume. And the scaling also tells us that wide angle effects are usually the largest of all GR effects because they are not controlled by Hubble, but actually controlled by whatever the size of your survey is. In particular, as I was saying, once these effects become important, we also expect the window to become important because this is exactly the scale where window function effects and integral constraint effect become important. So we do expect then wide angle effects to be suppressed by the presence of a window function. And in particular, this allows us to, rather than writing the full correlation function, the multiples of S1 and S, to do a series expansion in S over S1, because we know that on scales where the series expansion break, then the window function will take care of it. In particular, in this expression for the multiples and in the series expansion, because I'm using the S1 as the line of sight, I'm breaking the remaining symmetries of the theory, which is azimuthal symmetry, which is just a reflection of the pairs. And in particular, this generates dipole in the correlation function, which does not contain any new cosmological information, but it's just there because of our choice of parameterizing the theory. And in particular, for those of you who are interested in the intrinsic dipole that could come, for instance, from Doppler effects, you may want to use another line of sight. And so write both your theory and your estimator using a different line of sight, which is more symmetric for the pair of galaxies. And in that case, you can just repeat all the arguments that I'm showing you here and Enea is showing in his talk for any other line of sight of your choice, because the theory is still easy and the measurement is still a Fourier transform. So let me just show you how this works for our survey. So you see here in the top panel, so this is the ratio between the monopole, the full calculation, and the expansion for different orders in S over S1. So the blue line, S over S1 to the 0, is the flat sky limit. We also see here that we have two lines. So one is this 2 pi over R survey, which is sort of the scale where we expect to see deviation between the full calculation and the series expansion. And there is another scale, which is this 2 pi over R max, which is the true maximum separation we can measure within our survey. And this is basically the minimum K we can measure. So anything on the left of this panel actually is not measured on the left of this line. So the first thing we notice is that at least for the monopole, flat sky is a very good approximation. It's only inaccurate to a few %, even for very, very large surveys. And this is just reflecting the fact that to get larger surveys, we need to go to larger redshift, and so moving to higher redshift reduces the impact of wide angle effects on the power spectrum. And then we also see that basically the series expansion converges very fast. So even though this was an asymptotic series, the fact that we do have a window function removes all these problems, and the series converges very fast. If we look at the quadrupole, the situation is pretty much the same. Here, the comparison is a bit more complicated because, as we were saying, the quadrupole crosses zero once we include the integral constraint, which we always do because it's a very important effect. But even that, we see, for instance, here on the left, which is the worst case scenario, so where we expect wide angles to be the larger, the series expansion is accurate to 10%, basically, if you go to high enough order in the series expansion. And this 10% is actually pretty good because the cosmic variance scales much faster than all these wide angle effects. And so this is just shown here. And this is true in particular for the even multiples. If we, for the moment, exclude lensing from our discussion. The other thing which we said in the beginning is an approximation that we take, and we would like to test it, is whether or not we can get away with an effective redshift rather than doing the full integral over the redshift survey. So these two plots show you this approximation. So here we have the monopole evaluated at effective redshift divided by the true monopole where we do the full integral. And so again, we see that this is an extremely good approximation. So basically to the extent that this survey can measure, this is going to be accurate to a few percent. And we have two sets of lines, because as I was saying, we can do the more careful calculation of having one effective redshift for each multiple. And so these are the continuous line. Or we can sort of do something simpler and define just one volume weighted redshift. And this is shown as dashed line. And we see that basically also this one works pretty well. The difference is some amplitude, which very often we can just reabsorb in a changing of, for instance, the bias parameters. The other effect I would like to talk to you about is lensing, which is notoriously complicated to deal with in Fourier space. So this is the expression, and this is just from the fact that this is an integral over the line of sight. So there's just no way that we can associate formally one single Fourier mode to this object. But in our formalism, this is not a problem because we do have the correlation function, and the power spectrum is just the Fourier transform of the correlation function. So here I'm showing you some example. So this is a very low redshift survey where we expect lensing to be basically negligible. This is indeed what happens. So this is the RSD correlation function, including the window and the integral constraint. And we see, comparing to the red one, which is the lensing contribution to the total, this is basically negligible. It's 10 to the minus 3. If we go to higher redshift and the width of our surveys increase, then the lensing can accumulate more along the line of sight. And so we expect this effect to grow. This is indeed what we find. So if we now consider a survey between redshift 1 and 2, or 1/3 of the sky, always keep that in mind, the effect becomes a few percent. So it's still pretty small. To get the effects of order 10% or larger, we really need to go to redshift 4 or higher and have very large extent over the redshift direction. So this is for the quadrupole, pretty much the same story. Here, it's important to keep in mind that, for instance, the integral constraint for this survey is actually making the quadrupole becoming negative. So the effect of lensing is even more reduced compared to the monopole. So just to summarize this first part, so we now know how to compute the exact average of the galaxy power spectrum, including all possible effects in theory, in observations like window functions, and we also know how to deal in principle with other observational effects like, for instance, systematics and other things. And as I said multiple times, Enea will present our full story. For current surveys, we just checked again what we knew already, which is if our constraints are on the order of FN of 20, these jet effects are not yet important. And I was not able to show you if these effects are actually degenerate with FNL in a full galaxy power spectrum analysis, because the missing ingredient here, or in a Fisher calculation, is the covariance. So we need to have an expression for the covariance of the estimated galaxy power spectrum, including the same effect we put in the mean of the power spectrum. So we need to have GRFX, window function, internal constraint, and all of these included in the covariance before we're able to make any statement about the degeneracies of GRFX with primordial Gaussianities. But this is future work that Enea and I are already doing, and we hope to have some result pretty soon to show you. So let me just change gears and talk you and tell you about the constraints, the actual constraint that we obtained with EBOS data. So this is the most recent one and also the best one that we have nowadays from large-scale structure alone. And so the motivation here was to say, okay, we do have a theory which we understand pretty well. So now let's move on to the data analysis side of the story. And in particular, we know that primordial Gaussianities constraints are dominated by cosmic variance. What that means is that the statistical error is actually of the measurements of the power spectrum is the main source of uncertainty for FNL. What this also means is that in principle, the Fisher matrix, which only takes into account the statistical uncertainties, should provide a very good estimate of what we can actually do in the data. On the other hand, experience is that when we actually do analysis in the data, we never get back the Fisher numbers. And this is true even for the BAO, which is sort of the simplest of all possible analysis. There are reasons why this is so, for instance, unaccounted systematics or modeling issues that we are not considering our Fisher. But from the point of view of primordial Gaussianities, we're only looking at linear scale, so we should know the theory extremely well. So if we don't get the Fisher numbers, it means that our analysis was not optimal from a statistical point of view. So we need to do the right thing. And do the right thing means two different aspects of the problem. So one is that we need to do the full inverse noise weighting of the data. And this was something which was sort of formalized more than 20 years ago by Max Tegmark and collaborators. But we don't do it very often because for standard cosmological analysis like BO and RSD, which look at only high K, then the standard FKP or Yamamoto estimators actually converge pretty fast to the optimal answer. So we don't need to do the full inverse noise weighting of the data. On the other hand, for primordial Gaussianities, which live at the low K, then these estimators are not optimal. So they're not treating the statistical uncertainties in the best way. The other missing ingredient is that we never do the optimal signal weighting of the data. And this is something which is routinely done, for instance, in CMB when they try to analyze primordial Gaussianities. So can we do that in large-scale structure? Can we do better and actually reach the Fisher values? So how do we do that? So what are the guidance, what is the guidance that we have to do that? For primordial Gaussianities, intuitively, we can immediately see what we would like to do. So imagine that I'm at the Sloan telescope and observe my past light cone, which is populated with galaxies. There are a few things which I immediately recognize if I want to measure primordial Gaussianities. The first one is that the scale-dependent bias is proportional to the primordial values of the gravitational potential, which is not a function of redshift, whereas the standard Gaussian piece is a function of redshift and it actually grows with time. So what that means is that I should go further in redshift, where the ratio between the Gaussian to non-Gaussian piece is actually smaller. So where we can give more weight to the primordial piece. And the other thing which I would like to do is not to bin my data in redshift, because by doing that, I immediately remove all the information on the radial modes, which are a lot of modes within the survey. So formally, the answer to this question mathematically is, in statistics, is called an optimal quadratic estimator of the data. So given a set of galaxy position, delta of x1 and delta of x2, we need to define this object, which is the sum over all positions of galaxies, weighted by their inverse noise. This is the inverse covariance weighting, and also weighted by the response of the signal covariance matrix to FNL. If you do the math, then what you end up with is this expression that I wrote down here. So the optimal estimator for the for FNL is nothing else than the estimators that we already had for the multiples of the power spectrum. But now we have to weight each individual galaxies by some number. And this number is the response of each galaxy to FNL. And so you see indeed that some weights are this W tilde proportional to the B phi, which is the response to FNL. And the Gaussian part of the signal has to be weighted by D of Z. And D of Z is a decreasing function going to high redshift. So these weights do exactly what we were hoping they would do. So they downweight the Gaussian piece going to high redshift. Whereas in contrast, the standard analysis has all these weights set just to 1. So we did this in EBOS, and some key features of EBOS are shown here. So these are 180,000 quasars in redshift 0.8 to 2.2. There are more quasars at lower and high redshift that we didn't use. Their number density is extremely low. So indeed, this is not really the best sample to test optimal estimators, but this is what we had. And so it's always noise dominated at any scale. It's a small fraction of the sky, so only 5%, which is sort of guarantees that all the effects that we were discussing earlier would not be relevant. And it doesn't show any significant contamination from foreground systematics at low K, at least in the monopole. So these are our measurements. So this is the standard measurement, what we call the FKP. So this is the monopole. And these are the optimal measurements. So we have 2 sets of those because as I was showing you very quickly, the response of the galaxies depends on this unknown parameter P, which takes a value between, let's say, 1 and 1.6. So we repeat the measurements for both. And you cannot see it, but basically all these points here in the optimal estimator are slightly shifted upwards compared to the FKP analysis, which is just saying that we have increased the effective redshift of the survey by a tiny bit by giving more weights to high redshift galaxies. I'm not showing you plots for the quadrupole because we couldn't use it, because we saw a clear sign of contamination in the quadrupole that we were not able to remove. This is not a problem because we do this analysis at fixed cosmological parameters, so that basically the shape is just fixed, and so we don't need the information in the quadrupole. So this is what I was just saying. So we increased the effective redshift. So this went from 1.52 in the standard analysis to 1.64 in the optimal one. And just to show you that this effective redshift approximation works extremely well for a survey like EBOS, always within 1%. And this is the same also for wide angle angular effects. So how much do we expect to improve? Because it's important that we do have a benchmark in mind from the Fisher matrix. So we can use the simple linear theory, we just argue. And so then we need to compare the optimal analysis with the standard FKP analysis. And so this is shown here. So this is the uncertainty that we expect by combining north and galactic caps as a function of the K-max included in the analysis for different values of K-mean. And we do have different values of K-mean because we wanted to check whether or not some scales would have to be removed because of systematics. And so by comparing the dashed line with the continuous lines, we see that basically the improvement is always in the range of 20–25%, which is a lot. Because if you translate this into values of area and number of objects, this is more or less 30–40%, which would be extremely expensive if you now want to all of a sudden just increase your survey by 40%. In the actual data, we do not find the improvement we were expecting from the Fisher matrix. We find 50% improvement, and on top of that, we do not reach the Fisher value. And I'm going to comment at the end why this could be the case. So just to show you the final posterior, so this is the posterior of the standard case. So at 2 sigma, the standard case at 95% confidence level, it goes from -41 to 39. The optimal case instead goes from -51 to 21. And so this is indeed around a 50% improvement. So this is the best constraint using large scale structured data. And it's only 60 times worse than the CMB. And I'm saying only because keep in mind that we only have 5% of the sky of very noisy data compared to the 75% of the sky of the largely noise-dominated planet maps. So indeed, what we have shown is that if we could use all the quasars up to redshift 3.5, we could actually already get to FNL of order 10. And these are data which have already been collected, but the systematics are not yet completely understood. And in particular, in the final data release, the DR16, which came out earlier last year, which is 3 times more the area. So in principle, we could reduce by another square root of 3 our uncertainties. So we could really get down to 5. So this is already something comparable to the CMV, which we could do in the data right now. Let me just summarize. So as I was showing you, the road to improve over the CMB is very narrow because there are a lot of things that we need to understand. And in particular, optimal methods are going to be crucial if we want to achieve the FNL over the 1 benchmark that I was saying in the beginning. Spectroscopic survey are still the sort of best possible probe. For instance, the number that I was showing you with 5% of the sky and 200,000 quasars yielded better constraint than 50% of the sky in imaging with 1 million quasars. So spectroscopic surveys are really instrumental in getting FNL over the 1. Depending on the data set, we do find that the optimal estimator improves between 15 and 40%. And we could actually already be comparable with the CMB if we understand the data, if we understood the data much better than what's currently available. And for next generation of survey, which is what we all have in mind, things like DESI and Euclid, the data are not going to be noise dominated at large scales because the short noise is sufficiently low. So we do expect to have actually much larger improvement from the optimal analysis. And finally, we do not reach the Fisher matrix. This is what I was saying earlier. And there could be 2 reasons for that. One is that we do not do the full inverse noise weighting properly. So we need to sort of improve on that aspect. We only did the signal weighting in the proper way. Or it could be that our treatment is sufficient, but there were unknown foregrounds in the map, which are affect our measurements to 10, 20%. We were not able to detect them before. So just a take-home message for the 2 parts of the talk, we do have clear strategy to get to FNL local over the 1, which includes having a clear prediction for the observed galaxy power spectrum on large scales, including all possible effects, both in theory and in the measurement. And we need to couple our understanding of the theory with actually optimal method that saturate the signal to noise and the Fisher matrix information. And we have already shown that on noisy data, these methods already improve by 20%. So this was all I have to say. And thank you, and hope to talk to you soon during the conference. Bye-bye.